Thank you, Nishant, and good morning, everybody. I'm going to talk about differential scanning calorimetry and its applications for a few different things in cement-based materials. Let me tell you, I won't have pretty pictures like David showed you, but that should be okay. So, calorimetry, differential scanning calorimetry basically examines how the heat capacity for material is changed by the temperature. Lots of different applications in cementitious materials heat. But basically what you do is to heat or cool a certain sample and you measure the change in heat capacity as a function of the heat flow, which is measured in terms of temperature. So there are two different types of differential scanning calorimeters, very broad characterization. One is called a heat flux DSC and the other is called a heat flow DSC. Heat flow is more of power controlled DSC where it directly measures the heat that enters and leaves the sample. And there's feedback loop with a calorimeter that keeps the temperature within the material constant and measures the power required to do that, very similar to your isothermal calorimeter if you're measuring hydration. In a heat flux DSC, it measures the heat flux, the flux being the amount of heat that passes through a unit volume or a unit area in a unit. And then you base that with a reference material, which is generally sapphire of known properties, and the difference is used to find out what is the heat capacity. So these are two basic ideas in which differential scanning calorimeters are based. There are variations of this, of the same idea, but slight changes in how they measure it. The fundamental physics remains the same, the measurement techniques slightly. So, heat flux DSC is typically a single furnace design like you see on the right side. It is less sensitive to small transitions, they can heat and cool at lower rate, but for cement-based materials where we want the transitions to be known at that range, we are fine. Whereas when you get to polymers and materials with very, very sensitive glass transition temperatures, heat flux DSC might not be very effective. You may have to do heat flow DSC, which has a very precise temperature control, accurate enthalpy heat flow calculations. It directly measures the heat flow, not based on a reference sample. So those are the differences that you have. And then of course there's modulated temperature DSC, where you can apply a non-linear heating or cooling rate. You can separate the kinetic data from the thermodynamic data using a series of heating cooling steps, but again very commonly used in the synthesis of polymers and the synthesis of materials that require very careful control of how they change the temperature. So put in this is from Perkin-Elmer, a few comparisons between heat flow and heat flux DSC. You can see that heat flow DSC has lots of high performance, whereas heat flux is moderate performance. Again, moderate and high are relative qualifications based on what you need. But for cement-based materials, depending on what your need is, both of them will work. So here is a typical calorimetry curve as a function of temperature. And what you see is heat flow, exothermic or endothermic heat flow, heat released or heat absorbed as a function of temperature, and it measures the energy change. And as you do that, temperature and the power, therefore the area under the curve will give you the energy per unit mass or sample that you've put in. And that energy change, or the energy changes, and there could be multiple energy changes in a material depending on its constitution, depending on the different constituents that melt or solidify at different rates. You can have multiple transitions that you can see, and therefore you use those transitions to understand what is the effect of temperature on different phase transitions that happen in the material, how much energy is needed for different processes. So endotherms, generally in heat flux DSCs, endotherms are used down, so endothermic is that and exothermic is up. In heat flow DSCs, sometimes endotherms are done in the positive scale because they result in increase in power supply to sample, but that's basically academic interest. You can tweak in all the newer DSCs, you can just tweak the axis to suit what you want. But this is conventional representation of how you would read a DSC diagram if given otherwise, and if it's not mentioned what exactly it is. So one of the important things that you measure is a specific heat or heat capacity, which is the amount of energy that a unit of matter can hold. Use a sapphire standard, like I mentioned. Sapphire is very stable, doesn't become contaminated, so you get a very stable, consistent signal all the time. And what you see here, if you melt a material, if you heat a material, you can find out the onset of melting. You do derivatives of these curves to figure out these exact points. You can start to find out the melting of the material, peak melting, where the melting ends, and if you cool them down, you can find what is the point where freezing starts, the freezing ends, and so on. You see a slight difference. So the phase transition temperature in heating is slightly different from the phase transition temperature in melting. That is partly a function of the fundamental mechanisms that happen, because when you're heating something, you are looking at liquefaction of a superheated solid. So this is basically a solid becoming a liquid. But if you go the other way, it is solidification of a supercooled liquid. Then, so if you remember your basic solidification theories, you have to have a nucleus that forms. You need more driving energy for the nucleus to form and to get a particular size and then grow around it, which needs some more driving force. So this thing you will definitely see in all of the DSC diagrams that you learn. But you can change it if you use an extremely small sample. With cement-based materials, it's very, very difficult to use that small samples. If you use extremely small samples and use extremely slow heating or cooling rate, you can just lay them really one on top of the other, but you'll see the difference here is about 295 versus 303, 304. So depending on, I mean, you can bring that narrow to a couple of degrees Celsius. So enthalpy, like I mentioned, is the energy required to heat a material to a given temperature, the area under these curves based on the baseline that you do. And you can use enthalpy of melting to estimate both purity and degree of precision. And then derivative curves, like all relative measurements, derivative curves help you to better interpret the data in terms of calculation limits, in terms of data resolution, all of that. First derivative for stepwise transitions like glass transition temperature. Second derivative to exactly resolve the shoulders into peaks to find out what is happening at those different temperatures if you want much more precise determination of what is happening in the material when you heat or cool. So let me quickly show you one application using DSC, and we've done this with phase change materials. Phase change materials are materials that change the phase from solid to liquid and absorb heat and then release that heat in the reverse transformation from liquid to solid. So these are combined sensible and latent heat materials that have been used in our past work to control thermal cracking in concrete. So a lot of heat of hydration that is released is absorbed by the phase change materials in changing its own phase rather than causing changes and cracking the concrete because of temperature differentials. So you have a solid, that's your sensible heat, and that's your latent heat capacity where energy is absorbed or released at a relatively constant temperature, and then the phase transition happens to liquid. So energy is absorbed and stored and released when the temperature is changed. So we have done this to do thermal crack control in pavements and bridge decks. We have used it to make coatings and paints for building envelopes. We have impregnated this into porous inclusions for thermal management crack control. We have incorporated this into 3D printing elements for structural thermal, combination of structural thermal building envelopes. So very broad range of applications for this materials. So this is how a micro-encapsulated phase change material looks like. Two different phase change materials from two different manufacturers. One is basically an agglomeration of a lot of different smaller phase change materials into a larger body, whereas it's much more dispersed. But both of them are paraffin wax based. One has a very high wax content and therefore obviously will have a much higher enthalpy. The capsule, residues, pore to shell ratio, so basic ideas. And here are the phase transition temperatures, the DSC spectra, heat flow curves for both those samples. Both the manufacturers say that this is about a 25 to 27 degrees Celsius phase change temperature, which you see that generally for both the phase change materials. The E1, the smaller one, because it has higher amounts of wax, as you saw, it has a higher amount of heat capacity, which is expected. So this is what happens in heating, and this is the cooling spectrum, the reasons for different heating and cooling. This is a very crude, fast rate curve. I mean, again, we had another PCM that looks at a 35 degrees Celsius phase change because for hot temperatures, 23 doesn't work. When your temperature is very high, you need a slightly higher phase transition temperature. And here is the integral curves to find out the energy absorbed. So two of them have two different enthalpies, 250 to about 300 joules per gram. Right, so here is heat flow. So now once we had the phase change materials and once we had characterized them, we use them in cement paste with different amounts, and you will see that with respect to the amount of phase change materials that we have used, you can see an increase in heat capacity of those cement-based materials. At about 25%, you're getting about 5.8 joules per gram of the entire cement paste. If you have 25% of PCM to replace in cement, that's a pretty large number. You don't want to go there in applications. In applications, you want to limit to about 3 to 5%. But again, this is such a high number. Just to see, are we scaling it and are there losses as we go? So what we have found out is that the onset temperature is about 21.9, completion temperature is about 29, endothermic peak node about 26.2. It's a 25 degrees Celsius as dictated by the manufacturer, eventually ends at about 26, which is okay. And then what we have also looked at, used DSC, is to look at the stability in cementitious systems. You have a very alkaline core solution, you have an organic material that goes in, these are micro capsules, some of these capsules can leak when you mix with concrete, and nowadays manufacturers are coming with much more robust and reliable encapsulation strategies. But if it leaks, what happens? So here is heating and cooling spectra. Here is the heating and cooling spectra for a certain phase change material, and then just showing the heating part alone for different amounts. And then here is the measured enthalpy, and we calculated the enthalpy, theoretical calculation of enthalpy based on the materials that we have and the melting temperatures and all of that. What happens if we start to look at stability? So this is all in calcium hydroxide, sodium hydroxide solutions, and see here, and with immersion time, you really have not figured out much of change in enthalpy. So in cementitious core solutions, the microcapsule, the encapsulations are fairly stable even at 30 days of immersion. In all these different solutions, it doesn't do anything much. For sodium hydroxide solutions with higher and higher molarity and up to 3 molar sodium hydroxide, still the enthalpy variations within 1 or 2%, you are fairly consistent. But the moment you have calcium sulfate, the moment you have sulfates in solution, you see dramatic reduction in enthalpy with increase in sulfates, and you actually start to see these capsules breaking and dissolving in different locations. This is in unreacted capsule. You can see lots of capsules breaking and reacting in sulfate solutions. Again, which we postulated to be the formation of melamine casings on the shell, which break them, release the PCM that contact the sulfate ions and form melamine sulfate. Okay. We used a few other techniques in conjunction with DSC. We used FTIR, we used XRD to identify that indeed is melamine sulfate that's formed. So another way to use it. We have impregnated PCMs in porous media. So if you have different types of lightweight aggregates that you can impregnate with liquid PCMs, now not microencapsulated, but really liquid PCMs, you encapsulate it, you will see the heat flow as a function of the porosity, basically, for different types of lightweight aggregates. And here is the specific heat capacity of the individual aggregates, and then the calculated and the measured enthalpy for different types of lightweight aggregates. Again, I should mention that it's a big function of the porosity of the aggregates, because the more porosity, the more absorption, the higher enthalpy you find, because more phase change materials get it. We can use this DSC information into thermal models to look at what is the thermal capacity of the materials, especially when you have a porous media where you've impregnated all these phase change materials. You can decouple lots of these different processes and find out using models. We've also used the DSC information to predict the actual heat development in a hydrating concrete pavement as soon as it is placed, and we've used this data to develop models for pavements with PCMs and to predict cracking and time of cracking. So you can look at a concrete pavement on a subbase, and you can use the basic convective, radiative, and absorptive heat transfer equations using these boundary conditions, different layers, with these PCMs. So basically what we have done is to have the ability, again, for aggregates and water, the heat capacity remains the same. For cement-based materials, you can take the heat capacity to be a function of hydration, depending on the hydration products that are formed, and with phase change materials, heat capacity is a function of temperature. You can input all this into a computational model and predict. So this is in Phoenix, the temperatures in July in blue and March in red. Somehow we changed the colors differently. Phoenix should be really, really red in July, not blue, but we just did that inverted. And then if you look at different volumes of phase change material and what happens with early age heat release. You can see here, that's a very early hydration heat release, and with that, with the amount of PCMs, you can really, really drop that temperature down for March and for July. So you can see here how we can use this to predict the section temperatures. Yes. I'm done, Nishan. You have 3 minutes, I've given you that. So you can look at phase change materials to do thermal phase transitions, melting, crystallization, glass transition temperatures. You can measure heat of fusion, heat of crystallization, thermal fingerprint of materials. So I just, to summarize, I put in all the ASTM standards that I could collect that uses this, so that, you know, if you want to do something that is very standard based, you can do that as well. Thermal properties of different materials, ASTM E793, E794. You can do the specific heat capacity of pure compounds or of mixtures, like what I showed you. You can see different transitions, and you can relate those transitions to different materials or different compositions that are present. You can determine the purity of a relatively pure substance. How pure is a substance that you have? You can find that out, because if it has an impurity, it will show a different relationship with respect to temperature in melting and solidification. You can use that to find out if your material is very pure. Determines phase separation. You can characterize a lot of different curing processes, typically with polymers. Glass transition temperatures of cured sample, residual material, all of that. If the transitions are very, very subtle and you want to separate the thermodynamic and kinetic effects of translations, you can use a modulated DSC where you use nonlinear change in temperature with respect to the rate. You can do that. You can assess thermal stability with ASTM E537. You can do kinetics of chemical reactions or decomposition, ASTM E690. So lots of different applications and different uses for this material. I should thank our sponsors for this work, who's partly funded by NSF, Innovation Program from the European Union, and Arizona Department of Transportation. Thank you very much.